Now what we just developed is actually known as the dis method. We took that function x squared over 2 and we spun it around the x-axis and created a bunch of disks and essentially added up the area of the infinite number of disks that makes up that solid. Now to elaborate a little bit more on exactly what the dis method is or how to use it, there's primarily two scenarios that you'll be working with. First of all, to find the volume of a solid of revolution with the dis method, we're going to use one of the following techniques. The first technique will be if we're going to revolve it about the x-axis. So if I have some function like I just did, it looks like this, and I revolve it about the x-axis, see, my disk will be in this direction. So what I'm going to be working with is my volume will be equal to pi times the integral from a to b, where I'm starting and ending. In this case, the previous example is 0 to 1, but it could be like 3 to 9, whatever, times, and I'm going to use capital R of x squared dx, where capital R of x is actually the function that represents the radius. Now, the other situation will be if you're going to revolve about the y-axis. See, I could take this same function and this time revolve it about the y-axis. And if I do, I'll get a solid that looks like this. Rather than this cone, I will have this bowl looking thing. Now, when I look at my slices, or if I consider my slices, it's going to be in this direction along the y-axis. So this is where my circles are going to be. So my radius is no longer a function of x, it's a function of y. So with that in mind, I need to modify this formula here, and I'm going to say that volume equals the integral, or pi times the integral, and let's say from C to D along the y-axis here of capital R of y squared dy, where R of y again equals a radius, but this time is a function of y, where previously it was a function of x. Now, when I first developed the idea of the dis method, I already did this particular one where we used x squared over 2, that's this function, and we revolved it around the x-axis, and we found the volume that this thing created. So now let's take a look at this, and this time let's revolve it about the y-axis. So I have f of x equals x squared over 2 see, it was 1. This is a half. Only this time I'm going to revolve it around the y-axis, so it's going to look something like this. Come out here to negative 1. So x squared equals 2 is right here. But rather than my radius being vertical, I now have this horizontal radius. So what I need to do is figure out what the function is that represents that radius. Well, what I have is y is equal to x squared over 2. That's this as a function of x. So all I have to do is solve for x to figure out what the function of y is. So this implies that x squared equals 2y, which suggests that x equals plus or minus the square root of 2y. So this is going to be R of y. So my volume is simply the equal to pi times the integral along the y-axis. Now I'm going from 0 to 1/2. So that'd be 0 to 1/2 of the radius squared, and that is the square root of 2y squared dy, which equals pi times the integral from 0 to 1/2 of 2y dy, which equals pi times 2y squared over 2, evaluated from 0 to 1/2. Clearly the 2's cancel. So that equals pi times 1/2 squared minus 0. So that's simply pi over 4. So again, it's pi over 4 cubic something. If I don't know the units, then I simply report it as simply pi over 4.